Hey folks, welcome to another InfoViz lecture. This time we're going to be talking about the dumbest way to be smart, or about machine learning for designers. The first question that should make you ask is, well, what does learning mean? What do you actually mean by a system, a machine that has the capacity to learn? What does learning mean in practice? This is a video of my then 1 and a bit year old daughter.
Mama, Daddy,
So what she is doing in that video is asking to be taken to the park. She was about 13, 14 months old at the time, and she has learnt that the front door and the shoes at the front door are what we do right before we go outside. She so badly wants to go outside, and she has learnt that the word bye-bye is associated with going to the park. She has a 14-month-old child. She didn't know at the time how to say, I want to go to the park, or even park. But she was expressing her desires with the information that she had available. How did she know to do that? How had she, a living creature that had 14 months previously not experienced anything, how had she built a sophisticated enough picture of the world to be able to communicate what she wanted to do? And every child does this, by the way. I'm not being like, proud dad, look at how smart my kid is. Every child has the ability to demonstrate their needs and their wants long before they have fully functional capacity for language. Katara, my daughter, in this has some words, but not the ones she needs to solve the task. But she has learnt enough about what she can communicate to get our attention and let us know what she wants. The pointing at the door alone tells you what she needs. And this, I think, can be used to answer that question of what is learning for our perspective, both for the perspective of the development of a child and for what a machine learning system can and should do. Learning is association. Learning is not so much about facts. Facts are just a way of keeping score. Learning is associating some things that you can perceive with other things that you can perceive. In that video, my daughter associated the door with going out. Perfectly reasonable, but that is an expectation, an association that she built with the world she had available. That, in some sense, is the kinds of things our machine learning systems can do. Because this is an association, right? Much less complicated one, drawing on many fewer factors, but this is an association between how much money you make in sales and the temperature of that day. Let's say that this is a chart of how much your ice cream stall makes, and when there is hotter weather, your ice cream stall makes more money. You may recognize this from year 8 or 9 mathematics. This is just plotting a simple line of best fit over some data. Each of these black points has a clear relationship among them. As temperature goes up, sales goes up. So we can plot a line of best fit, and we can use that to answer questions like, if the day was 21 degrees, if tomorrow is going to be 21 degrees, how much money do you think your ice cream stand will make? You can look at that and say, well, it'll be somewhere between 400 and 500, probably. You don't know for sure, but you can see that there's a relationship and there's not that much noise. So you can say, all right, 21, about 460 on average, but with a range of maybe 400 to 550, right? This is learning. We are doing predictive statistics, and machine learning, artificial intelligence as applied to learning from data, is really just predictive statistics. It's just gotten a little bit more complicated, because while that kind of learning is association, so is this. Girl in pink dress is jumping in air. Black and white dog jumps over bar. These sentences were written by a neural network. They were written by a machine learning system. Does that mean the machine learning system has the capacity of a human toddler? Not so much, because the machine learning system had seen tens of millions of these pairs of objects and descriptions, whereas the human had never actually seen that many labeled examples. The human may see many, many dogs and many, many girls in pink dresses, but is never explicitly shown, hey, this is a girl in a pink dress. All right, now this is a dog. And seeing all of those things over and over many millions of times let this neural network, which was made a couple of years ago by some folks at Stanford, let this neural network not just describe girl in pink dress because it had seen things that were or weren't girl in pink dress, but actually able to compose sentences, to write short sentences that best described the thing in that image. This may be much more complex and nuanced kinds of association, but really this is just the same association as the top image, sales goes to temperature, but with more variables involved. Many, many more variables involved. So let's take that example further and see if it'll help us understand what machine learning is and how it works. Let's say you, again, were the ice cream store owner, and you wanted to answer the question, hey, when do I put on a second person? When, on what days do I ask someone else to come in because we'll get enough demand that I need that second person? And maybe you say, okay, well, on days where I sell more than about $500 worth of ice cream, that means the queues are usually long enough that it would be profitable to put on a second person. So how do we, instead of fitting a line that predicts the money, how do we want to sort of answer the question, well, yes or no, do I put on a person? And now, obviously, you could take those predictions, that line of best fit, and you could punch it into an if statement and say, if it's over the 500 line, let's do it. But you could also let the data speak for itself if instead of fitting a straight line, you fit a decision function. Here's an example of a decision function. If 0 is no, you shouldn't do that, and 1 is yes, you should do that, and where you are in between is like the probability of this being a good idea. So 0.5 being, yeah, it's a toss-up. And 0.75 being, yeah, like 75%, that's a good idea. You can fit a function like this, just some arbitrary curve. Don't worry about what the equation of this curve is or how you draw it or anything like that. But you could fit this to the data. And instead of saying, all right, I want to know how much money I'm going to make, you want to say, I want to know whether we're in the white part of the chart or the green part of the chart. And you do that and it looks something like this, right? Okay, for those temperatures under 18, it's a virtual guarantee that you're not going to break the $500 mark. For those temperatures over 24, yeah, it's a virtual certainty that you're going to break that 500 mark. In the middle there, well, the probability probably scales up rapidly after you get past 20 degrees. This is the same kind of statistics, just with a slightly different function, right? Hey, I'm going to show some maths on the next slide. Don't freak out. A line, the equation for a line is mx plus b, where x is the x-axis value. The y-axis value is some number m, which controls the slope of the line, times x plus some constant b, which controls where the line intersects 0. You may or may not remember this. It's not going to be assessed for this subject. I'm just trying to put some context on exactly what's going on here. The line for that S-shaped thing, well, the formula for that is 1 on 1 minus e to the minus kx minus b. That doesn't matter. All it matters is that you can describe that curve such that there are a couple of parameters that you need to learn. Let's go and say instead of a line is mx plus b, let's call it kx plus b. K in the line is how high the slope is on your line, and b is where does the line intersect 0. Well, with the logistic curve, that k in the e to the minus k thing, that is how steep the vertical part of your S is. Does it rapidly change from 0 to 1, or does it slowly change from 0 to 1? And b is where's the midpoint? Where is 0.5 at? So you can do exactly the same kind of thing. What's the slope? Where does it intersect? If you just understand the maths a little bit. You totally don't have to understand the maths. I'm showing these to make a point, rather than to say, hey, look, you need to learn the equation of the logistic function. Machine learning is just a way to use data to guess what K and B are, or whatever other parameters there are in your model, the things that you need to learn in order to get a good line or to get a good one of these logistic decision function-y things. All machine learning will help you do is to make the best possible guess you can given the examples that you have available. All it lets you do is fit a curve to something. So you decide on a model, then you throw as much data at it as you need to produce a good model. Whether that is an individual curve, like the one we were just talking about, an individual line or an individual S-shaped decision curve, or whether it's a neural network. You might have seen a picture of a neural network that looks something like this. These are just neurons, each of which is part of making the decision. We're not going to go into too much detail about how they work. But the truth is, inside each one of those is a little decision function, is a little S-curve with its own parameters that are learned over the course of feeding it data. In this case, you learn the weights on how much to incorporate each of the different inputs and what should it output given those inputs. What I'm describing here is the structure of a network, not how that structure is learned. But effectively, this is the intuition behind how neural networks have always worked. Neural networks have been around for a very long time, by the way. This is what we might describe as a neural network now. But if you look at this is Frank Rosenblatt in like 1957 or something or other, working on the perceptron. I think Frank needs to work on his cable management skills, huh? Every one of these registers is connected to every other register. And if you actually have a look at the finished product, this is the size of a fridge, by the way. You can see on the right-hand side there, those are variable resistors that you can actually use to dial up how much the machine will care about each of those inputs from the diagram. This is a manually tweakable neural network from 1957, before people had good ways of automating their training. And that people actually fed data into it, looked at the error, slightly adjusted it, fed more data into it, looked at the error, slightly adjusted those physical knobs so that it got better at doing predictions. So let's say, how would you train something like this? This idea of training and looking at the error may be confusing some people. Let's look at step one here. You want to build a system that tells cats apart from dogs, and you have a simple decision boundary. So a line. You're saying, okay, dogs are on this side of this line, cats are on that side of the line, but I can move where my line goes. And in practice, this looks a lot more like one of those S-shaped curve things where there's a high probability or a low probability of dog, but you can think about this as just the midpoint of that curve, the point where it goes over 50%. More than 50% dog, more than 50% cat. If you've got two, you'll draw a line right in the middle and say, okay, anywhere on this side is cat, anywhere on that side is dog. You then show it another dog, and it'll adjust slightly. You can see the line in step two has adjusted slightly so that the other dog is inside dog. Then step three, you're going to put some more cats down the bottom. It's not going to adjust all that much. These are all inside the thing. Step four, you put that little chihuahua down the bottom there. It has to adjust where the decision boundary is in order to include that one, which it knows is a dog. It just got told that was a dog, in order to include that one inside the dog side of the boundary. And every time it sees a new example, it will update where it thinks the decision boundary is very slightly. Learning these associations in a machine learning context is just incrementally changing the structure of your model. And a model is just those parameters from before. It's just kx plus b. K and b are my parameters. They're the things I'm going to adjust. That's going to change where my line goes. There's maths behind how each of those things work and how you update them. But you as a designer don't need to go that deep unless you want to. There are resources in this video for how you can go deeper should you choose to open that particular Pandora's box. But all you need to understand is that when you show data to one of these things, it's just incrementally getting slightly better by reducing its error on the things that it's already seen. A little bit more maths on this one, don't freak out. The way you incrementally update that model is you say, okay, I'm going to take my old model and I'm going to add some small thing, my learning rate multiplied by the error. You leave your learning rate small just so that one example doesn't completely change your model. You can think of it this as how aggressive do you adapt? How much do you conservatively prefer your existing data versus aggressively chase new data? With a learning rate of 0.01, you adjust 1% towards any new example. And you multiply your parameters by how wrong they were, and then multiply by this learning rate parameter so you don't go too far, and then you adjust slightly in that direction, and that gives you your new model. Again, a model is just a value for a bunch of variables that we call parameters that make up whatever prediction you're using. You're predicting using a decision function, you're predicting using a neural network, you're predicting using some other complicated thing. That is the structure of your model, and learning just helps you decide where those variables are going to lie in the space of possible models that have that structure. So that's perfectly reasonable for just adapting a tiny decision boundary, adapting something simple like in that top version, where you have some clearly visualizable single function that takes you from your input to your output, where you're going to fit a single line, or you're going to make it a single decision using one of these S-curves, and you're just going to decide where to put it. What happens if you're doing something more complicated, like the neural network at the bottom? You don't have one decision function, you don't have one unit that's deciding what your output is going to be, but you actually have lots of these different neurons, each making its own decision that collectively make up the problem. How do you adapt your parameters of your model to meet new data when it's non-trivial how those things relate to the actual answer that you got because they're part of a complicated system? Well, it turns out that you can use calculus to do that. Calculus can tell you the contribution of an individual neuron to the overall error, and then you can back propagate. So you start with the last neurons, the ones closest to the output, you adjust them slightly, and then given how you know they did, you go up to the previous level and you say, all right, we'll talk about what was the contribution of each of these neurons to the error. All right, we'll adjust all of them slightly, and then we'll go back to the next layer and the next layer and the next layer. And it turns out you can use that to build very, very complicated predictors. We're not going to go at all deeper into how backpropagation works, except to say it's maths. It lets you figure out how much a specific part of your model contributed to the error, which means it lets you adapt the error, adjust your model slightly to fit that data as more data comes in. If you're interested in this stuff, there is a couple of links to 3 Blue 1 Brown videos in the description. Actually, I think they're in a playlist. I'll only link to the first one. I suggest you watch through a couple of them. They're simple and easy. 3 Blue 1 Brown is a wonderful mathematics YouTube channel. They're much better at explaining this stuff than I could be, and it's absolutely not going to be assessed in this course. I just think it happens to be a particularly fascinating rabbit hole to go down. So after this stuff, backpropagation was invented in the early 80s. It became possible to use things like the perceptron to solve much more complicated problems. And people used, over the decades, they used this kind of architecture, the neural network architecture, in more and more creative ways. They came up with tricks for how to use it to classify images, classify, say, handwritten letters as being one letter or one number over another. They came up with tricks to how to embed memory in the neural network in such a way that didn't break the calculus, and that made it easier to learn sequential data, be it stock market prices over time, or be it the sequence of somebody talking, audio data over time, or written language. All of these are now able to be input into neural networks via the various different tricks that we've learned on how to encode things. People also just benefited from how much faster computers got. There was an initial flurry of activity when backprop made it possible to have 3-layer rather than 2-layer networks back in the early 80s. And they were used for a couple of problems then. And then there were small improvements over time until the mid to late 2000s, when what we now recognize as deep learning started taking off, and people came up with other tricks, but also benefited from more powerful computers to let them train deeper and deeper networks with more and more layers, more and more stacks of parameters, and then more and more complicated ways of training, as is adjusting the model to fit the error and propagating the error back from each data point through each thing in your model to say, what was the contribution of this parameter to how we went wrong? Okay, let's adjust it just a little bit this way. And so these days, machine learning systems look a little bit like this. This is a Google tensor processing unit. It's a rack containing a whole bunch of Google's specialized hardware for doing machine learning computation. And if you look at this, you can't help but think of Rosenblatt's machine from the late 50s, right? Other than the fact that in the intervening 60 or 70 years we've discovered cable management, it's pretty much the same stuff. It's a wall-sized computer that uses specialized hardware to make decisions using many of these simple decision functions built into a structure that we call a neural network. Many, many parameters built together into a model that help you decide on things. TPUs can now be used as part of systems to cure cancer, drive cars, drive rockets, pretend to be people, write articles. All of these things are amazing. I should explain what a tensor is. A tensor is just an array with more than two variables. It's just a term that is used a lot in machine learning, because when you want to actually adapt all of those parameters, you end up with really big tables of numbers, and you have to do maths on them. So these are called tensor processing units, because they are processing units designed to explicitly work very fast on many dimensional tables of numbers. But how much have we actually changed? How much have we actually made progress towards this?
Mama.
Because I don't think we've really fundamentally done anything except take one specific part of what learning is, associating one well-defined thing with another well-defined thing, and just gotten an awful lot faster at making those associations. Yes, deep learning has meant that we don't need to be as precise with our inputs and our outputs. You can now use an image as an input, rather than in Rosenblatt's time you would have had to just use a number. But it's still fundamentally associating the distribution of some variable, an image, a song, a picture of someone's cancerous or potentially cancerous tumor, with an output. And while those outputs are getting more complicated, instead of just predicting categories, we can now construct whole sentences. It's still association in the most simple way. Now, I'm doing machine learning a bit of a disservice. There is the whole field of reinforcement learning that doesn't explicitly tell the machine what the answer to each problem is. It just gives it a score. So that allows it to learn a little bit more abstractly. And even more so, there's unsupervised learning, which doesn't give the machine the answer and just expects it to find structure in the data. But those are limited too. They have not, thus far, helped us to get to the level of flexibility that would be necessary to imitate a 14-month-old child, much less get anywhere closer to a person. In fact, I don't think we're beyond the level of a puppy yet. I think we're nowhere close to a particularly intelligent Labrador. But does that matter? Like, I don't think these systems are trying to be a human brain. It just means that we need to be careful when we use terms like artificial intelligence. Exactly how much intelligence are we embodying in these things? And that's the kind of nuanced answer I think you, as designers, should be able to give and understand when it comes to working with these things. What can a machine learning system actually do? How far has it gotten? That's going to change as technology progresses. Some of my examples are from 2017, and they have been absolutely outclassed by stuff just in the last 3 or 4 years. That's a lifetime in machine learning research. But we're still fundamentally at the stage of learning to associate one thing with another. But there's starting to be other things going on as well. It turns out that as of 2020, training a state-of-the-art language model, that is something, you might have seen these, it can read like a whole paragraph and then tell you what comes next. It'll take 300 tons of carbon, emit 300 tons of carbon into the atmosphere to train one of these giant models on one of those tensor processing unit kind of things in a data center. These take so much energy, so much compute time, so much storage that you can't really do them on your laptop. And to do it over and over again, to adjust these big matrices of numbers over and over again, is not kind on the planet. Now, of course, AI is not alone among interesting trends of the 21st century for using a ton of electricity and emitting a ton of carbon. The current reigning champion of wasting electricity in the name of compute goes to these folks. These folks have, of course, used a great deal more electricity and emitted a great deal more carbon in whatever it is that they do. Hodl gang. There have been other criticisms of the machine learning field as well. This researcher, Ali Rahimi, gave a very famous talk in 2017 when he said machine learning researchers don't even know why these different algorithms work. They don't have rigorous criteria for choosing one or the other. They just throw them at the data and fiddle with them until something works. What he was actually saying there is AI is alchemy now. Alchemy didn't really understand how metals worked or understand the chemical properties of any of the things that they were working with. They were chasing these dreams without having any underlying theory. And so they are saying, Ali Rahmi and many other people in the machine learning community are saying, look, you're just messing around trying to turn lead into gold. But the thing is, it kind of works. Like, I'm not harshing on any of this stuff. I live and breathe this stuff. It can do amazing things. It can create all new kinds of experiences, create all new kinds of products. Just don't believe that it's a magic bullet or any kind of intelligence. I'll leave you with this XKCD. So this is your machine learning system? Yeah. You put data in here, and then answers come out over that side. What do you do if the answers are wrong? Oh, you stir it. This is kind of where we're at. The pile is very big. It uses a lot of servers. But ultimately, machine learning hasn't come that far, theoretically speaking, from those machines in the late 1950s that learnt to divide one set of numbers from another set of numbers. That doesn't mean you're not going to get huge value out of designing with them and understanding how they work in the future. You just need to be realistic. I'll see you in class.